Okay, we're going to take a look at problem 12.2-5. It says for a flat tension bar with a stepped cross section shown in the figure, fillets are quarter circles, and they give an equation, and it says that capital D is equal to 4 inches and little t is equal to 1 inch. If the smaller width is 3 inches and the axial load is 15 kips, what is the maximum normal stress in the bar? All right, so let me draw this flat. Going to sketch out this geometry. We're going to have to use a stress concentration factor chart in order to determine our stress concentration factor to determine our maximum stress. All right, so it says capital D is 4 inches, little t is 1.0, and little d for part A is 3.0. So we need to go find in our book the appropriate stress concentration factor chart. I have found that, and so I will call it up right here. All right, if you notice, there's a lot of different curves on here, and these different lines are for different values of capital D over little d. Down on the bottom is this term little r over little d. We're going to need to find that radius of curvature, and they gave us an equation for it. They said little r is capital D minus little d divided by 2. So for our problem, that's going to be 4 minus 3 divided by 2. That's going to be 1/2. So that means little r over little d is 0.5 divided by 3.0. It's going to be 0.167 out to 3 significant digits. Okay, so we need two things now. We need capital D over little d. In this case, it's 4 divided by 3. It's going to be the 1.33 curve, and we need little r over little d. So 1.33 is pretty close to this curve right here that they're pointing to. Little r over little d of 0.167. Let's see. Looks like each of these divisions are 0.2, so this would be 0.12468. So 167 is pretty close to here. All right. So in order to kind of get the right line, I'm going to drag a vertical line over. There we go. I'm going to move this over here to about my spot. Okay, and you know, these are pretty approximate. So when you have one of these on a test or something, show your work, show your lines, and I understand that not everybody's going to read the graph exactly the same. All right, now we're going to go and we're going to bring that over with a horizontal line. And we should find the 1.33. Now 1.3 is the line. 1.33 is going to be a little bit above that, maybe about here. 1.5 is the next line. So I'm going to say it's approximately in that position. All right, so let's see where we're at. Here's on this axis 1.2, 1.4, 1.6, 1.8. 1.9 would be about here, so I'm going to call this about 1.85. Let's see what kind of stress we get if we have KT is equal to 1.85. K or KT means the same thing. So if you look over here, it shows us how our nominal stress is defined, and our maximum stress is calculated from our K factor times our nominal stress, which is the force they said was 15 kips, divided by little t times little d, 1.0 inch, and in this particular part of this problem, 3.0 inch for little d. So let's see what we get. 1.75 times 15 kips divided by 3 square inches, I get about 8.75 KSI. So that would be our answer for part A. Now for part B, it says if the bar must be able to carry an axial load of 15 kips without the maximum normal stress exceeding 8 KSI, what is the minimum width that can be used for this reduced width cross-section? So we're going to have to change this dimension little d until we get the right combination of values that gives this stress of about 8 KSI. Oh, and before I get onto that, I did make a mistake here. I need to correct this. I wrote down 1.75, but the number that I found from my chart was 1.85. I'm not sure where I got the 7 from, but this should be 1.85, and that's going to change my numbers just a little bit to 9.25 KSI for this stress value. So let me go ahead and just change that right here. Alright, so for part B, we need to find a different value of little d that causes our stress to be lower. We can kind of use our value here as a starting point. If we continue to the right, we're probably going to end up, we may end up with some higher stress concentration factors, depending on where our curve is at. If we go a little bit to the left, we may have a reduced stress concentration factor. Now, I don't know exactly which way is going to push us where right now, but let's just try capital D has to stay 4. Let's just try little d equal to 3.5. Alright, let's recompute our R value. So now this is going to be 4 minus 3.5 over 2. It's going to be 0.25. And then this is going to be little r over little d. It's going to be 0.25 divided by 3.5. That's 0.714. And then capital D over little d. It's going to be 4 over 3.5. It's going to be 1.14. Let's see what we get now. 0.714 is going to push us way over here. So let's see. This is 0.08. Okay. So let me recompute my little r. 0.25 divided by 3.5. That was 0.714. So should be a 0 right here. So if this is 0.08, 0.07 is about right in the middle. Just a little bit to the left maybe. And my capital D over little d line is going to be 1.14. This is the 1.2 line. This is the 1.1 line. So we're about halfway in between here and here. So maybe about here. Okay, 1.1 to 1.2. So maybe we're about in this position. So that looks like it's maybe 1.9. So let's see what we get. Sigma maximum is going to be equal to 1.9 times 15 kips divided by 1, and now our little d is different. It's now 3.5. Even though the stress concentration factor is higher, our nominal area has increased. So let's see what we get. I get 8.14 KSI. Okay, we're still a little bit high. Still a little bit higher than where we want to be. So let's try a different dimension for little d. And it's a little bit tricky. I'm not sure exactly which way I need to go, if I need to increase it or decrease it. So let's not change it too much. Let's just change it a little bit. Let's try maybe 3.4. If that's 3.4, then little r is going to be 4 minus 3.4 divided by 2. It's going to be 0.3. Little r over little d is going to be 0.088. Capital D over little d is going to be 4 divided by 3.4. That's 1.18. And so now we go to 0.088, which is pretty close to 0.09, which is about there. And then up to find just under the 1.2 line. This was the 1.2 line. So, it's just a little bit higher than 1.9, maybe 1.92. So our sigma maximum looks to me to be about 1.92 times 15 kips divided by 1 and 3.4. Let's see what we get. I got 8.47. Okay, so that's still a little high. So let's try another one. I'm going to run out of room here if I'm not careful. So 3.5, and then we went to 3.4, and so let's try something in between, maybe 3.45. So little r is going to be 4 minus 3.45 divided by 2. It's equal to 0.275. So little r over little d is going to be 0.797. Let's call that 0.08. We need capital D over little d, which is going to be 3.45 divided by, it's going to be 4 divided by 3.45. It's 1.16. And so we're right here. We are going to go up to the 1.6 area, to that 1.6 line. Now 1.1 is here, 1.2 is there, and it's kind of a big expanse. Halfway in between these two lines would be 1.15. So I think we're up just a little bit, maybe about there. So I'm going to call that one 1.87. So again, we're going to do our stress calculation. I won't write it down again, but I'll say it. 1.87 times 15 kips divided by 1 square inch, and then 1 times 3.45 to get square inches on the bottom gives us 8.13. Okay, so we're getting pretty close. So I would say that our dimension D is somewhere maybe a little bit less than 3.45, maybe in between 3.4 and 3.45. So I'll let you do one more iteration if you'd like, but we want to try to get somewhere just a little bit less than 8 KSI. Again, there's some variation here because you're reading a chart. It can be kind of hard to read good numbers off of these, but give it a shot.